thanks for the invitation. Thanks for this really nice workshop so far. I'm not sure what to take on being put right after Thomas with the reproducibility talk and now talking about quantum, which is explicitly not reproducible. In fact, that's the whole point, it's not reproducible, but we'll see where this goes with the discussion then. But also, like everybody else, I thought I ought to add a couple slides about where we come from with the performance tools and where I came in with the performance tools, which also started quite a bit ago. At TUM, actually, when I joined TUM as a PhD student, it was before Michael's time, actually, but Thomas was already there. We were looking into cluster computing. That was a big thing back then. This is how our clusters looked back then. So 6 monitors, nice next to each other with 6 towers and connected with a whole bunch of cables in the back. So that was cluster computing back then. We did this with the SCI, the Scale of Coherent Interface. The project was called SMILE. The S stood for the SCI interface. And then we also started putting up a software stack. Sorry, I only found this in German, but I'm sure that I think you can get the idea. We had shared memory parts of it. We had message passing parts of that. So a typical software stack, which actually kept haunting me for the rest of my career, these kind of stacks. And we'll see a couple more examples why I say this. My PhD itself was about here, but building a shared memory environment and making this performant, which is kind of ironic considering that I'm now working with MPI mostly, and kind of back then I was advertising everything shared memory, but I guess that's what it was. The library itself was called Hamster, and since then I was known for cute and cuddly logos, but they kind of luckily subsided at some point. But that's what we're kind of working on, kind of making performance, and that's kind of where the tools part came in. We actually also had effort back then to actually do hardware monitoring, which also a couple mentioned already. This is the SCI card that was developed actually at the chair by someone else. We had a really good hardware developer back then. And then building on top of that was a monitor adapter card, which actually was able to track all memory traffic. It was a shared memory card, so there was a lot of shared memory traffic going on, and we could track that, and we could actually find out exactly what's going on in the traffic at that point. We were able to do graphs like this, where we could find out which pages were accessed by which nodes in the system, so we would exactly know how the NUMA distribution was in this distributed system. And we could even go further down. We could look into a single page even. So which addresses in the page were accessed by which parts, and we could actually pull this apart at that point, again, because we had this monitoring part in that. I think, and that's also where we started interacting with the APART project back then, because we looked into how can we connect this to OMIS, which Thomas already mentioned before, how we can connect this with the old infrastructures about the tools that were developed back then, and how can we bring these things together. And this continued even afterwards when I went to Cornell. I myself then got really involved into tools when I went to Lawrence Livermore. That was 2004, believe it or not. And there I started working for a project called Open Speed Shop, which was a new performance tool that was kind of developed back then. Worked very closely with Bart's group on kind of the base instrumentation infrastructure. So it was at a time where you guys started pulling apart Dynans into these multiple components, and we started using individual components of that. I think it was a very good collaboration. I think it was also very nice tools. It was a little bit over-engineered, but aside from that, I think it worked fairly well. So this actually stayed with us for quite a while. But now this is kind of has been retired, and some parts are still working in the labs on that as well. But then more interestingly, I think from the research point of view, we started pulling up kind of the ideas, what can we actually do with the information? I mean, there was a lot of performance tools out there. This is Tau, this is Vampire, and the question is, what do you really learn from this? And we started to look into how can we visualize the performance in a better way, and that's the PAVE project, the performance visualization project we started at Livermore. And I think this was one of the most stunning results that we had. So this is a timeline for a simulation of an aluminum jet stream coming down here on the left side, getting into some chaotic behavior. And we contrasted it to the L1 cache misses and the floating point operation, and we mapped it similar to what Bernd and Felix showed on the cube part back onto the domain. And we can kind of clearly see there's a part of this which clearly corresponds to what happens in the simulation, so that's clearly data dependent. But then there's also things like these red dots, and those are clearly not data dependent. We're able to distinguish between the two. These red dots ended up being problems, but it ended up being caused by the MPI library. It's a single core in a particular node. So each node had a single core which was responsible for reduction operations. And that's what caused these higher cache misses here. And so we kind of had the 2 rows was always one node. And then each second row was then that particular core on that particular system. Well, where was exactly this one? We never found out, but this is the decision that the MPR library made, basically. So based on that, we then started developing a whole bunch of performance tools with the focus on visualization. There was the boxfish tools, which took the topology back then from the blue gene LPQ lines, where we had these nicely high-dimensional tori. We could map them and kind of see how can we slice topologies through the cube or through the torus. We looked at better visualizing traces. We wanted to get these things unraveled. That's also why the tool was called Ravel. We kind of lined these things up, but you could kind of lateness information in this as well from a performance visualization point of view. And we had a tool called MemAxes, which took memory traces and mapped them to the NUMA nodes, to the caches where they were originating from, so you can kind of see if you had a mismatch in the topology setting that you had. So all these tools kind of came out of that area, out of this PAVE project, and I think it was actually very, very interesting and very successful. In fact, we're actually still working on the MemAxes part that made it back onto the German side. So we're still working with some of the EuroHPC projects now to extend this MemAxes to have more information, also to include GPU information. Some new tools actually came out of this. So there's about a bit history about my performance tool part. But then something else happened. I was in Munich. And now I want to say now something completely different, because at that point, it was short before the pandemic, there's a lot of excitement about one thing, quantum computing. And so all the physicists got together. There's a lot of physics institutes in Munich. There's also for different lines of quantum computing. And they wrote this big proposal to the Bavarian government about the Munich Quantum Valley, bringing all physicists together to develop the quantum computer. So this big fancy device which will solve all problems that we have and be much better than any other system that we have. But they also realized they have to talk to the system somehow. And so they wanted to have something with the cloud, because the cloud, they knew what that was and they wanted to connect to the cloud. So they wanted to have some kind of connection between the two. And so they needed some kind of portal in between. And who do you call if you need a web portal? Your local HPC center, because there's the expertise for web portals there. And so we started talking with them, and then we kind of convinced them pretty quickly, look, you don't need just a portal. You actually need a little bit more than a portal. There's actually a whole software stack that needs speech as well. And that's how I got into the game of working on quantum computing. I'm not a quantum physicist, I'm not a quantum expert, but we are really working on bringing these two things together and what is the software needed to actually make this all work together. And that's kind of the main point of the talk for today. And so why are we actually looking at this? Well, I'm not going to give a full tutorial on what quantum computing works, just a little bit to kind of motivate this. Right, so we're working on a system based on quantum mechanical principles here, which follow Feynman is not worth doing if it's not quantum, because everything is built on quantum at the end. You have two major concepts here, superposition, which means you have multiple states at one time. So you can basically explore the whole state space at one time until you measure it, and then you get one or the other. Which one depends then on a probabilistic nature. So you do this very, very often until you get a good overview of what's there. So reproducibility, forget it, right? There's just statistics there. And then the second thing is entanglement, where you can connect two states together and get one influences the other, and that's kind of where the power of the computation then comes from. Looking at qubits, these qubits then can be superposed with the superposition part and or entangled. And you construct your algorithms by basically having operations on that make the superposition and the entangles work. Then you read it. At that point, it collapses. You get a 0 or 1. You can never read it again. So you have to start from the beginning. You do this multiple times until you get a statistic results of what you want to see. And then you hopefully have the right answer here, right? You program with so-called gates, which they always say it's similar to what we see in our classic computing gates, but it's actually something completely different, because our gates in classic computers are physical things, and here they're operations that you apply. So you have like physical qubits, you have these lines, and then you apply these operations. That's how you draw these circuits, and at some point you measure them, and that's basically when they collapse and where the computation ends, because afterwards this is not there anymore, or it's kind of collapsed to the particular state when you read it out. And then so basically you have these operations on qubits, and different systems have different gates. So there's also not just one type of gates. Each kind of type of quantum computer has different gates, and so you need to know what kind of quantum computer you have. And then why are we doing this? Because we're all on the quest for what's called quantum advantage. The idea is there's some algorithms that require exponentially less steps than the comparable classic algorithm. That's the promise, at least, that they have, and there's a few algorithms where we know this is true. Very few at the moment. They hope, of course, there's more algorithms, and we're going to get to that at some point. So that's kind of the thing.
So you guys are looking specifically at a gate model, not at an annealing model?
Yes.
Okay.
Yes. So the ones that we are working on in the Munich Quantum Valley is explicitly gate models. And I have this afterwards, it's superconducting, it's ion trapping, and it's neutral atoms. Those three. So even photonics, which again is something different in that sense, right? Yeah. And then why are we doing this? Main application domains, where we think, or where the physicists think they can actually get a lot of advantage out of. There's a simulation of quantum system that goes more to what you just mentioned, Bart, the annealing part, where you have a quantum system and you basically model this in a quantum computer and you just let this play out basically because you have a quantum system emulating a quantum, physical quantum system. But then optimization, machine learning, this is kind of the other thing where this kind of, the idea is to have this parallel search across all possible scenarios, and you can do this all at once, and you do this statistically over a certain amount of tries, but that number of tries is not exponential to the state space that you would otherwise have to explore. So that's the goal. And so there's a bunch of approaches there. There's a bunch of toolkits already out there. There's also these ideas where you basically go through a classic computer and you do some experiments, you measure them, you kind of adapt the experiments, and you kind of have this loop until you have a result for some of these algorithms. So this is kind of the ideas people are trying with that. The problem is we still have a very small number of qubits. I mean, we all know that, even though when IBM is kind of touting their 1,000 qubit system, even that's still very small. The systems are noisy, and typically the more qubits people have, the more noisy they are. And so this is very, very hard to get large number of qubits that are not, or there's as little noise as possible. So this means this again adds to the non-reproducibility, right? Because if you have noise, you know, you have to do it even more often to get statistically something that's useful. Only very few algorithms. Programming works totally different. I'm be honest, I have not myself not fully understood how this really works, how you take a problem and map it into the quantum space, because it's really a different way of thinking. And at the end, these systems basically are still physics experiments, right? And if you talk to the physicists, they have their labs and they have the grad students sitting around the experiments, plugging in cables, measuring things, tweaking things. It's not a real computer yet in that sense, even though we're trying to get to that, of course. And then this is kind of why they pushed for this Munich Quantum Valley. It's a large initiative by 7 institutes in and around Munich. So we also have Erlangen here, so that's part, the rest is Munich though. So we have Bavarian Academy of Sciences, we have TUM, we have LMU, the big universities, and then also several Max Planck and several Fraunhofers are involved in that one as well. And the idea was from the beginning to not just focus on one modality, but actually on 3. As I said, superconducting, ion trapping, neutral atom. And then we kind of, at the end, were actually able to squeeze the HPC in there as well. That was in the beginning not foreseen, but we kind of made clear that at some point you're going to need this as well. And so this is kind of the tagline now. Mission of the MQV is to kind of architect, design, implement, and deploy full stack quantum computing. So there was a big emphasis of not just doing a single experiment, but to really to build this up full stack so it can be spun off into companies. Of course, in and for Bavaria, because it was funded by the state of Bavaria, plus additional grants. And in this MQV, there's a project which we call QDESI, which I have the honor of leading, which is the Quantum Development Environment, System Software, and Integration. So where we started looking now, what kind of software pieces do we actually need? How can we connect the users to the actual systems, and how can we build, again, this nice picture of a stack that we know so well from the other HPC side in here as well. And we're doing this kind of as an open source software stack for these full stack computers, and we're doing this for MQV, but also we have a lot of external funded projects as well on the EU side, on the German side, on the Bavarian side. And we're trying to spread, of course, this one stack across all systems. It's supposed to be a stack that's adaptive and kind of works with different backends, works with different modalities. And we're kind of also trying to engage the community, of course, here to make this work, and not just for our systems, but across different companies and different initiatives also as well. Also on the European level, we're looking at the same stack there as well. And here is it again, the stack picture. That actually, I wasn't the one drawing that. That was actually came from the application of the grant that, that when it was written. You had, again, the stack where you had the hardware on the bottom. You have the user application in there, and then a bunch of technology parts, kind of the blue part, and then kind of the softer part, and it's kind of the orange part. We also go from operating system programming languages all the way to quantum algorithms and the theory part. And the QDESI part sits basically here. This is there's a software piece really connecting the hardware platforms to the application side. We're looking at compilers, optimizers, and tools, whatever that may mean in quantum, right? We're still trying to figure out what a tool in quantum really does. I mean, there's some tools for verification in there. There's some tools on kind of showing that things actually work. We're not looking at performance yet, right? We will come at some point, hopefully, but this is not quite the goal yet. We're looking at how can we make this multi-user environment, so we cannot just have one user use the system at a time like a physics experiment. We can actually put this into a compute center so multiple users can access to that. And with that comes resource management. So how do you actually schedule these things on these systems? Yeah?
What are you optimizing for performance?
Sorry?
What are you optimizing for performance?
Well, the beginning, the first part is you get to this a little bit later, but you need to first map the general part to the back end. You need to understand which gates you have and kind of make it possible at first that you have a valid code that runs on a target machine. And there's some simple performance metrics like number of the gate, like circuit depth or circuit width that you're trying to optimize for, but it's not anywhere close to what we consider performance engineering, I would say, on the classic side. But so yeah, it's a performance in the sense of width, but more the depth of the circuit, but there's actually not so much performance, but if you have a circuit that's too long, it will simply be wrong, right? And so again, it's more actually making computation possible instead of making it faster. Yeah?
So maybe add this, I would say you also optimize to reduce noise. That's another aspect.
That's true, yeah. Again, but not so much to make this even faster, but to actually get something useful out of that, right? So it's more a correctness thing than a performance thing. And then the second part of QDESI is to integrate it with existing systems. How can we deal with the host platforms, the control platforms, and then also how do we do the analysis of the data coming back from the quantum computer, and how do we actually make this possible as a real accelerator for HPC, where we really see the future. This is a very specific problem they can target, so it will also be part of a classic workflow with a quantum component to that. So how can we bring these together and make this work as really as one system? And as part of that, we have 4 focus areas, which were in the project were called central tasks. So one is actually in the program environments, one in the runtimes and operating systems. We actually have a hardware project as well, where we're designing FPGAs to control the quantum computer. And the last one then is the integration into the HPC. And we never got them rid of the cloud system. It's a proper remote access, right? It's not really a cloud in that sense, but physicists love the word cloud. And so the question is, where do we actually stand now? And we have done a lot of progress in this. We have spun these 3 kind of lines up as part of the Quantum Valley. There's a lot of basic research going. At the same time, we have started kind of looking around how we built up the software stack. But I think this still captures us very, very closely and this is basically is always the excuse you have on quantum systems, right? Don't ask that question because it will collapse afterwards. Where do things really stand? Well, if you ask the companies, this is the future of quantum computing. This is IQM. This is the Finnish German startup building superconducting ones, beautiful boxes, widely spread on an expansive compute floor, and then some actually blue gene Q racks in the back, right? If you can actually notice that, what that is. There's that. And if you look at IBM, it looks like this. So it's a beautiful design.
Do we have any numbers for these installations concerning energy consumption?
Yes and no. So but those are renderings, right? I mean, this is artist impressions how this will look like at some point, right? The main thing here is the cryostats. And the cryostat take about 50 to 20 kilowatts. And the actual electronics inside, 2-3 kilowatts, is not that much. We're right now paying purely for the cryo part. Yeah, no, sure, of course. If you look into reality, this is more what it looks like. And actually, I think this actually looks more cool than this, right? I mean, this is kind of boring and sterile, but this is a real picture from the Max Planck Institute for Quantum Optics, where they're focusing on neutral atoms quantum computer, and they built them up here. So this is basically a quantum computer with the optics put around it and experiments for that. And as cool as it looks like, so visiting them is actually really neat, because you go in these completely dark rooms and they kind of pull these kind of sliders apart, and you kind of see this kind of optics kind of mounted wildly on a table. Yeah?
Sorry for that. I think if there was a physical representation of climate models, it would look like this.
And it looks cool, right?
And so there is screws.
Yeah, and I love the glasses too, right? And so of course this will not work in an HPC center, so how are we supposed to bring this in the center? Right, so we have been working on what we decided to call the Quantum Integration Center at LRZ. So LRZ is part of Munich Quantum Valley. It wasn't on the list before explicitly, but it's part of the Bavarian Academy of Sciences. And the question is here, how can we get this into a state, a setup that we can actually use? And so this was our first one. This is an IQM-based system. This is the cryostat again, so this is the cooling part. Here's the electronics on the side that actually controls the quantum system. And it's getting into kind of a rack form, is at least somewhat handleable. Then we lately was able to procure an AQT system. This is from a company here in Innsbruck. So you asked me for the photo. So this is the real photo from the lab taken yesterday. This is an ion trapping computer. And they were the first company that actually put this into real racks that are self-contained racks. And in this one, you actually have a power consumption of about 2 to 3 kilowatts for the whole system. So you can plug this into a wall plug and can do quantum computing, because there's no cryo part in there. Right? There's literally just a couple lasers and a couple of front systems in that. So this is now installed in one room. We're putting some HPC next to that, so we can actually also connect it to the HPC. But the beginning was literally, how can we bring this into a room in a computer center so we don't have to make it look like this, right? And that was kind of the first thing, working with companies to get that going. And so this is kind of a first way for us to get our feet wet. For those of you who are not familiar with the quantum setups, it is something that I struggled in the beginning, because it's very hard to actually get information, because for the physicist, that's not the cool stuff. The quantum part is the cool stuff. Everything else is just engineering that you have to do. But this is basically how this looks like. This is the cryostat. This is an example of a superconducting systems. You have the whole cryo part to it. So the refrigeration part, that's where we spend these 15 to 20 kilowatts. This is where we can cool this down to almost 0 Kelvin. At that point, so minus 273 Celsius. So it's about 10 millikelvin, 10 millikelvin that we get the system down to. So we can have a superconducting part of that. Of course, it goes through stages here in that part. And that's the beautiful chandelier we always see, right? This beautiful golden chandelier with all these loops in there. Loops are just cables to get the microwaves from here to here. That's all it is, right? There's nothing fancy in that except to get the engineering right. And then you run the microwave cables here, and there's a computer on that side where you have the microwave generator that then goes out to the system. And basically, this is what you program. This at the end here, you can't program anything. That just reacts and builds the quantum states. Here's a picture of this beautiful chandelier. And again, this is just cables. The chip sits somewhere down here, gets looped in with some cables. Again, they were handed down. It's like down here is a small chip. It's about this size then, which actually can contain the quantum part. It looks something like this. I didn't find a better picture here, but this is actually a picture from a D-Wave system, which is actually an annealer. But the system is very similar in the sense that you have this chandelier here, a little bit smaller. You have the chip down here. The chip looks very much like a semiconductor chip, slightly different technology, but they have the same basic type of fab lines. And you actually produce these superconducting qubits here on these kind of chips. And the chips hangs down here, and you can connect it. You control everything from the outside through these microwaves coming in. So there's actually no internal control architecture. So that's why I always kind of find it funny when people talk about this being like assembler, or like back then when we did programming like assembler. This is much lower than that. An assembler language, a von Neumann machine, can react to something happening on the machine. Here you have all the control outside. You just put these pulses in, and then you see what the system reacts to. And the whole thing is noisy. So because we're not fully superconducting, we're not a totally 0 Kelvin, there's always an uncertainty here. And so that's also why it's called NISQ machines, noisy intermediate scale quantum computing. So we basically accepting the fact that this is noise, and we're trying to deal with that through what Frank already mentioned, error mitigation mechanisms, or kind of better circuits that have less noise, less errors, to get some results out of this part. And this is not just true for superconducting, this is true for other ones as well. So this is an example with neutral atoms. Here it's not superconducting 0 Kelvin. Here you have an array of atoms, literally a glass plate where they said simply throw a couple atoms on, slap it together, and then they arrange the atoms the way they need it through a bunch of lasers that go into that. And at the end, there's actually literally a camera taking a picture of the atoms, and you kind of find out where your atoms are, whether it's a 0 or 1. After your computation, you get your result from that. Besides that, you again have a control system here. In this case, we control lasers, we don't control microwaves. Same principle though, you send pulses in, the pulses get modulated into lasers and get shot onto that thing. This is actually a real picture I got from the physicists. And you can kind of see the whole thing is controlled by a little tiny laptop, and there's a thin wire going to the supercomputer, right? So that's kind of the idea that initially they had when we talk about integration. And so this is kind of the thing where we're trying to get them away from and kind of say, can we just connect this directly up so we have lower latencies, we have direct throughput, and we don't have to worry about this. The answer we then get sometimes, why do we need this for 20 qubits? Our answer is, I thought you wanted to go higher than 20 qubits at some point. But so this is kind of the discussion we're having with the physicists at that point. Even though I have to say the people at Max Planck, this is an old picture, they understand this by now, and we actually have a very good working relationship on bringing these things very closely together. So again, similar structure, just a different control, different types of qubits, but the principle is very much the same. You have an external control system, and then again, you have a classic compute in here in the control system, and also here that kind of controls everything. And ion trapping looks again very similar. That's also based on lasers, and also there, it's always the same thing. You have a control system that creates some kind of pulses, and we need to make sure we can control the pulses the right way. And so then the thing of it that we always get, and so particularly from the politicians, so this is great, right? So if you want to build this and fund this, at some point this will get rid of that, right? Because quantum is so much more powerful than HPC. And that's kind of where we always throw up the warning block and say, no, the quantum computer will never replace HPC because it's very specific to particular algorithms. Quantum accelerators are part of HPC, is yet another accelerator technology that we can use now that we're coming to the end of Moore's law, to becoming the end of scaling gets harder and harder, right? We see the specialization, and this is one extreme form of specialization, I would say. We're trying to really make the point that this is not replacing HPC, it's not contradicting, it's not competing with HPC. You really have to see that together. And so we kind of working on the term of HPC-QC, really integrating these two things together. Why do we do into quantum computing? Because we want to get faster, right? That's always our goal for high-performance computing as well. And so we just want to add this to the supercomputing portfolio. And so this is kind of the strategy we're kind of pushing from the LSE side, both on the Munich Quantum Valley side, but also on the European level. The idea is this is not viable, particularly as we grow, because the control system's getting more complex. At some point, we have to worry about data staging and data post-processing. Where do we keep the data that goes in and out of the quantum computer? With growing number of qubits, that actually increases dramatically in the sense of the width of data that you need with repeated experiments and the states you potentially have. Again, this is targeted to very specific workloads. You saw these couple of algorithms in the beginning. For this, we hope it works very well, but then we always need something around that anyway. And then we have a tight integration that we need for some what called variational algorithm. That's the example that I had, where you have this really tight loop of doing experiment, changing a setup, doing the experiment, changing the setup, and you have kind of an optimization algorithm already running on the classic side to help find the right spot on the quantum side. And then, of course, we need to have also the compilation for that part. We need to compile quantum circuits to the point that we can execute. Those algorithms by themselves are very, very expensive. To do the optimization right, it comes basically down to topology mapping, things which we know from the classic side are very expensive. And also here the question is, can we actually use some of these HPC resources directly to help this while we kind of wait for the quantum results? We could actually already compile a quantum system there. So these two things can really work nicely together, and this kind of integration we're trying to push as well. So the idea is to have quantum computing as accelerators for HPC workloads. Basically, we have either the idea, can we do this with as fine-grained kernels as possible and kind of integrate them into larger workloads? And we're trying to kind of take some of the lessons where we have learned from other accelerators like GPUs and FPGAs. We're actually trying, can we use some of the very similar programming approaches? Or we also see these larger disaggregated AI hardware like a Cerebrus chip or similar. Can we use some of those technologies for that as well? As a consequence, we're really trying to see this as one thing. So HPC and QC as one single system. But this requires, of course, to kind of have the tools and models to extract these application components. What is actually quantumable? What can we actually extract and send to the quantum system? We need to have an easy access. Also, people on HPC, at least that's what we always try to write, so not supposed to be the computer science experts, but the domain scientists. Right now, this is really hard with quantum because you actually kind of need to be a quantum physicist to run this. And that, of course, is not scalable either. We need to have a single programming environment, including the tools then, of course. And we need to have also close physical integration so we can actually run directly from there into the, from the quantum system into the hardware of the HPC system and back. And then the other one, which is something a little bit underestimated, I think, is that we also need a unified user access and management. If you really want to schedule these things together, it's really hard if the quantum computer is like far away, managed by a different group, managed by a different user management thing, because the scheduling doesn't work together. It's very hard to do kind of a common scheduling across that if you don't have this kind of unified access or unified management part. It's another reason why we really want to bring this together as a single system. And so here's an image, a kind of picture when we started designing this. So this is actually one of the compute floors at LSE. So these are standard racks over here where we have several big standard clusters. And we actually starting to place quantum systems directly, not just in the integration center, which is a lab environment, but directly into the compute floor. Things like you cannot put them onto raised floor, which we typically have because there's vibrations, so you need to put the things down in the foundation part. You need to have compressors and all the cooling mechanisms there. You need to suddenly deal with gas handling and like handling of helium or liquid nitrogen, which all kind of our facility people were like, what are you doing to us, right? How are we supposed to handle helium in this kind of environment? And this is kind of the things we had to go through to make this work. This is the first system that's currently being built up, the first production system, and then the European system will be put right next to that. So that's how it actually looks like. This is a physical picture now from inside that room. You see the standard racks here, you see the cryostat here, and then the control logic rack right next to that. And you can go straight into the HPC and networking here. This is kind of also the list of systems that we're currently looking on the superconducting side. What you saw before was a small 5-qubit R&D system. We now have also 20-qubit R&D systems. We can retrofit the old one against a 20-qubit chip. This will be also a 20-qubit chip, but kind of in a higher production quality. And it will be running into the dark center. And then on the European side, we're going to add a 50 and 100-qubit system also on the compute floor. There's a whole line of quantum computers that are rolling into LSE as part of German and European funding in this part. And then, of course, since we want to integrate it with HPC, we had to connect them as well. So we're testing, of course, we're connecting the small ones with our test beds. And then as we grow the systems, we're also growing the HPC system next to it, and we're going to start integrating them directly to SuperMOOC and Xi phase 2, and at the end to our ExaMOOC system that is planned as well. So we're going to have, again, the quantum system directly connected to this specific HPC system in the same management layer, in the same control network, so we can have the integration really play out also on the production side, not just on the lab side. But for this, we have to play in the lab first. And so here's kind of a picture of what's happening right now as we're kind of finishing the construction of our labs. There's a cold lab with a space for up to 4 cryostat, and there's a warm lab which currently houses a cryostat because this one construction in Germany takes forever. And so this one was kind of in construction for a long time. So this will be moved over here. In the meantime, we're building up our cluster over here and then the trapped ion system that I showed you before. And that's actually a current picture. So the construction actually in that warm lab was recently finished. So you see all the new piping up here for the cooling systems and so on. This is currently still our small test system that will move into the other room at some point. Here's again the AQT system, and this is where the space where these here are the spaces where the cluster will actually sit So we can connect them directly between the two systems. It was also time to get there though, because when you see already AQT did a very nice job of putting them into a rack. Also on the IQM side, you see the stuff goes into like standard racks with the rear door cooling and things like this. This is not common, because then, as another fun anecdote, when you ask the physicist, we need this in 19-inch rack so it fits into a compute center and we can make it work with all the other equipment that we have. The answer is sure, we can put this in a 19-inch rack. That's no problem. We have that already. Right, and so you get a picture like this of the 19-inch rack, which of course then still has to be transformed into this part. The other thing we're doing in Integration Center is to connect it actually also to the telemetry. Right now it's still a bit open of what actually influences your computation in a quantum computer. What has an impact on it? Where do you get the errors from? And so we're starting to instrument the whole room. Temperature sensors is one part, magnetic waves another thing, vibration, occupancy of the system, power draw of course as well. Temperature, by the way, not just on one line, but we're doing this in every 10 centimeters from the ground up to the top of the ceiling. And we're trying to figure out what is the changing conditions actually. And we're piping this straight into a data center monitor, and so hopefully we can then compare it with the error rate that we see. Is there correlation with the environment, and hopefully we can get a causation from that and find out what actually impacts it, where do we have to spend money and effort to get it stable, and where doesn't it influence it, right? Right now they're kind of all over the place because nobody knows what really the impact is, and so we have to try this all over the place. So we do have a full IoT infrastructure for that, where we run like sensors on Raspberry Pis and little of these temperature sensors that mounted here on this whole stick. So this is kind of an interesting project by itself, and that runs into operation data analytics, and we're doing this through the DCDB, the data center database, which is already in production on our HPC systems and monitors them, and we're now adding the monitoring of these quantum sensors as well as the workloads of the quantum system, so we can have this all in the in one system here. And then of course we want to connect it to HPC. So right now the way this works typically is you have your chandelier with your chip on the bottom, you have the microwave controller. Those actually talk Ethernet. That's the main thing that we can have access to. That one is connected to a quantum access node, and this one we're now connecting to the high-speed network, in our case InfiniBand, but it could also be, of course, anything else. And ultimately, we want to actually run the cables to down here to the actual cluster, so the cluster can directly talk to the quantum system with that have the tightest possible integration. This is the hardware part, of course, but this is, of course, not enough. We have to have really a full-stack solution. With that kind of coming back into the software part, we kind of listed this out into infrastructure, hardware, software, applications, and then also the culture is very important. Right now, we've been talking about the top part so far, how to get the infrastructure right, how to get the hardware right. But then the other big piece, and this again, coming back to QDESI, is how to get the software right. From having right now more like glue scripts that kind of send something off over an HTTP channel to a remote system, how can we really get to single source programming with the right scheduling, with the right control logic and the right standardized interfaces. And so, going now a step back, so how does it look like right now? You have physicists, typically individual researchers, that use their Python with like, for example, Qiskit or Cirq or something like this, and they control their quantum device, which is in their laboratory. And this, of course, has a bunch of problems if you want to take it out of the laboratories. For one, we don't want to target the physics users. We want to target the discipline users that want to use the quantum computer. We need faster toolkits. Whenever we talk about this, we say we don't want Python in our critical path on the performance tool chain. And they was like, but for my 5-qubit system, it works just fine. And I said, well, scale to 1,000 and 1,000 MPI nodes and start 1,000 Python scripts at the same time, you probably run out of memory. And so that's something we need the faster toolkits. We're trying to integrate this into like a C-based toolkit. We also need more computational capacity to run these more and more elaborate optimization algorithms. We need to be able to make this more standardized, so we cannot just connect to the one quantum interface in that particular lab, so we can actually connect to a whole sea of devices. You saw we already have 2 modalities at LRC, and we're planning at least on 2 or 3 more. So we have the breadth that we can target. We need the ability to also have this near quantum compute for these quite with these tight feedback loops. And also with that, we need multiple backends. We want to just talk to one quantum device. We need to talk to multiple quantum devices. So what we want is this, wide user communities that want to use quantum computer, connect to a lot of devices on the side, and we want to build the software stack in between. And again, we're seeing this as part of HPC. So we want this HPC user communities, and we want to have this all integrated into HPC environments. And with that, we we're in the process of developing the Munich Quantum Software Stack, MQSS, that has this connectivity from the user community through the various pieces down to the different modalities that we have. The picture now has ion traps and neutral atoms, so we're obviously looking at superconducting as well. We're trying to integrate also emulation environments into this as well, so that we have the software for small experiments. We can also do this part. And so starting from left to right, first of all, we're talking different programming models. Of course, we're going to start with existing ones like Qiskit and Penny Lane. We want to integrate those. QLM, this is the solution from Eviden, formerly Atos, the quantum learning machine, has their own level abstraction with our users starting to use. We want to pull this up. And then we're also looking at new approaches like, can we repurpose OpenMP for that? So can we make the quantum computer a target offload for that? That actually works relatively well. We have a prototype for that. You can actually write a script and have in the text a quantum piece written, which will then be taken out and then sent to the quantum computer separately inside the OpenMP. OpenMP is not quite ready for that because you're mixing languages a little bit too much, but the principle could work very well. And of course, also looking at domain-specific support. I think the main thing where we need to get to, and that's what we're working hard for, is to start decoupling this, right? I mean, there has to be, if you look at Qiskit, there's a Qiskit solution with a Qiskit runtime system that goes to the Qiskit provider from IBM. And that works very nicely because one person designed this from end to end, right? But then you can't add all these different new programming languages, or at least when you add them, it starts getting kind of tricky. So can we decouple this, what we know too from our classic side, different programming languages, different compilers, and kind of mix and match that to different runtime systems? I think we need to get to there as well. One way we're trying to push for that is we're looking at different intermediate representation, particularly looking at QIR, which is the so-called quantum intermediate representation, which is an offshoot of the LLVM work. So there's several companies got together, Microsoft, NVIDIA, Quantinuum, Rigetti, I think 7 companies, and Oak Ridge, and LRZ joined them last year as well, to define a kind of an industry-wide standard for this intermediate representation that also matches what we're doing in classic computing, so we can actually represent hybrid programs the right way. So this is something we're currently pushing for that, with the hope of pushing this decoupling of the software stack forward. And one thing, for example, what we're trying is, this is our first attempt at this, the quantum programming interface, the QPI, where we would like to have, right now, similar abstraction as Qiskit, but integrated into some code. So you have here some C code. You can now create a circuit. You can kind of put something into that circuit. Then you can actually run the circuit. You can measure it. So you can add a measurement to that. You end the circuit, and then you can execute that. So it's very familiar from what we used to do for GPUs with OpenGL, right? We basically build up kind of a script that you can package it up as part of a C code, and you can ship it out, and you can actually read it. So the first attempt to bring this into a single source kind of environment where you don't have to have different sources. You can run this as part of an MPI code, you can ship this back, and as long as the interface behind it, the runtime system, allows you to schedule that, that actually works then together. And so the way we kind of see this as a sketch, you have a typical HPC part, you log in, you start your compute nodes where your Slurm daemon lies, that window starts the HPC application, can be an MPI code, right? You have things like CUDA, you have GPU accelerators, and QPI would be just another library you look in that then connects to the quantum daemon, which is part of the infrastructure of talking to the quantum system. Then they coordinate the right way and they send this to the quantum backend for execution. Right? So it's another library approach, very similar to what we know from other accelerators, with, of course, the additional complication that there's only one quantum computer and not 5,000 GPUs, right? And so there needs to be some scheduling, some coordination, of course, that has to be done by this backend. So this is kind of the language side. Then, of course, we also need a web portal. Our physicists still want the cloud access. And for some basic experiments, we don't care about latency. Where you want to do is over the web-based access that actually works fairly well. Also, that is basically complete and in a beta phase where we have our Bavarian Quantum Portal where you can get tokens, you can get user management for that. This token you can then copy, put into your scripts. You can get basically a provider similar to what you know from Qiskit. You can write, in this case, a Qiskit script that then gets executed on a quantum computer. You can have this graphically represented here, and then you get, this is the output from the quantum computer. It's a 5-qubit system. This was the old system. And here you see already what because you're doing this a certain time. I think it was 1,000 shots. It's like, it should be about 1,000. And you get the numbers between 0 and 31 back, because you have 5 qubits. They can be, after you read them out, everyone can be 0 or 1. It can be between 0 and 31. And you build a histogram of that. So you run it 1,000 times, and the value 0, 0, 0 came out 309 times, and the value 1, 1, 1 came out 174 times. And so those are probably the most likely answers that you want to get out of the system, right? So this is actually a calibration test. If the machine would be fully calibrated, 50% should be 0, 50% should be 1. You can see there's a couple things where they're not fully calibrated at that time, right? And where you see some errors in that part. But that's kind of the idea, what you would do, 1,000 shots, and then you can see where your statistics takes you.
Frank, is that good enough for your work here?
So it was a first test system. We definitely hope that the production system will be a little bit better. But of course, if you now think about, do this as 20, 50, or 100 qubits, those strings get very long, the histograms get very difficult to handle. So at that point, you start having a kind of a measurement readout problem by itself at that point. So we'll see where we're going to get. Then, of course, we have the HPC part, where you basically submit what we had before, your regular HPC job. Then that creates the backend part and then sends off the stuff to the quantum side. It's kind of what we had with the QPI or with the OpenMP target. That has to get into a scheduling part, where you now start having access from both sides come together. With a scheduler, which then also talks to the HPC scheduler. You want to have this co-scheduled on the right thing. You want to pick the right quantum computer if you have multiple ones for the right problems. You want to have the right target selection as well. You want to put this onto a hardware device or simulator. If you want to put in a hardware device, is this a script or a circuit that's better for ion trapping or superconducting? So there's some machine learning actually that we're doing to figure this out, which target system is actually the best for the properties that you need with a particular quantum device. And then also we're looking at different scheduler technologies which make this work, because right now we're playing with Slurm, but we have the feeling that Slurm will not be flexible enough to actually help this work. Slurm will probably stay on the HPC side, but for this intermediate layer, we're looking at seeing how can we augment this. And then we're coming actually into compiler infrastructures that we're going through this QIR part, where we then have a compiler with the appropriate toolkits, optimizers, verifiers, whatever you need at this point. And here again, putting something similar together than what we know from classic systems. Is LLVM based, is QIR based, so we can actually do this. We have compiler passes that we have in there, and we can basically with that load individual passes into that, very similar to what we do in a classic compiler infrastructure. And then this whole thing together then is labeled as the quantum resource manager, which then basically is a single process that we can address from the outside. And this is kind of the compiler-based infrastructures, again, LLVM-based. We have first a bunch of passes that we drag from a database of passes that we can provide. The first ones are device agnostic. So we have this without picking the quantum compiler, the quantum system first. Here we then pick the quantum system, and then we have another set of passes which are specific for the quantum computer on the specific gate sets or specific properties, which qubit is better than the other one at what day of time, right? I mean, there's a bunch of stuff that flows into this. What's very different to HPC, all of this currently is at runtime. There's very little we were able to build, or that people are building forward into like a static compile time. There's a lot of effort being put into that, but so far we're running all of this at runtime, so basically all JIT compiler with the matching problems, of course, in point of latency, throughput, and similar things. And then we have a backend part, and that talks to the particular backends where we can have and address the superconducting or the ion trapping or whatever we have on the backend. And here we're currently trying to find an interface that is work across the modalities, working with the 3 different groups in the Munich Quantum Valley, and we're also trying to, of course, go to the wider community and that, and can we have this interface so we can have the right execution, the right query of information for this dynamic compilation part, and also how can we do calibration and kind of maintenance of these systems in an automatic way. Also here we need to have some kind of trigger mechanisms that we can also grab from the outside. And so here we developed the QDMI, the Quantum Device Management Interface, as a platform-neutral API. It's a C-based API, so it's basically down to the metal, this is the idea. And then there's a core implementation that has all these backends as a plugin. And I'm not going to go through the source code, don't worry, but just to give you a feeling, so we're actually starting to have this initial prototypes. And if this looks a little bit like MPI, this is probably not a surprise. So this is kind of the same idea. You have an init finalize, you have sessions in here, and basically trying to take whatever we learned from MPI and make it a little bit better in this part. And when you have the ability, first of all, to set this up, to find your devices, then you have the right thing to actually control the device, where you can create the right structure to pass over.
Yeah. Is that a typo? Back to one slide. Previous, the first one that had the that one. Is that not supposed to be QMPI? Is it at the bottom, second from the bottom line? Is it?
Oh yeah, that's a typo. Good point. Good catch.
I thought maybe there's a quantum MPI standard coming up. We didn't know about that.
It was correct until you read it. No, that's definitely a typo. Good catch. Thank you.
Absolutely. You got it in seconds.
So anyway, the other part is that basically to schedule this onto the quantum computer, and we're going to run through these APIs just really quickly. And then the other one, we have these abilities to query. So this is actually to query the device. What gates do you have? What are your properties and what are the gate properties? So we can get the fidelities for every single gate. So we can find the best gate to circuit to put a certain qubit on to have the best, what Frank mentioned before, to get the least error rates, because we know there are good qubits and bad qubits. And certain part of the computation are more sensitive, so we put them on the good qubits, and the other ones we put on the bad qubits because it wouldn't matter so much. So these kind of things all need to be read out live out of the system to steer back into the compilation process, right? And so that's why this interface is here to do that. And the last part is then the ability to do the calibration part. And so this way we now end up on the right side. We can actually now control this. We now have the feedback part also ready, what we call the figures of merits and constraints, so we can figure out what to be optimized for. We need to query these fidelities out of that with the other part of the interface. And then this is the picture that we have from before. Now we run this backwards to the query process into the compiler passes. Of course, at this point, we're platform specific because we're reading the data from a particular platform. So this only goes to the second loop of passes, but then we can actually use this then to kind of drive the compilation process and optimize for the good and the bad qubits in the particular system on a particular day and particular wind and temperature and which subway runs by at the moment and things like that. And these figures of merits basically, so this is kind of a high-level sketch. The idea is that you have these properties and you have this across the different settings and you can read those out and you can start comparing with that. And that's actually currently really a heavy discussion between the software people and the physics people, the kind of what are these figures of merits? What do you want to have in this matrix that is of interest, that actually influences the compilation part? Which sensors can we even provide? And so this gets very specific also to particular modalities. So this matrix will never be a full matrix. This will be definitely be a sparse matrix because certain systems can provide certain gates, certain properties, certain fidelities. But this is the idea that the QDMI will actually able to handle that part. And if you now could step out again, this now comes the computer science part again into that. We want to make this in a way that we actually start separating these concerns in the infrastructure a little bit more than what we have doing before. It's not a single platform that goes to a single backend with a single software stack, but to have the software stack here, this is the part in blue, and be able to kind of put the right plugins into this part, to find the right system, to put the right compiler passes, to write constraints and metrics that you want, the right backends. And so you can have this generic infrastructure and you start loading these passes in and with that customizing it to a particular platform, to a particular modality. And once you select, for example, a particular backend, you would get loaded the right compiler passes, the right FOMAC libraries, and the right backend would be activated. And with that, you can drive the two-part. But the infrastructure is generic. And with that, be able to start in the separation of these concerns, to have separate programming models. All the toolkits will be separated out, and the backends will target a particular platform, but then can use this whole thing here up front as well. And the idea is to even go to the point that is mapping to pulses will also be pulled into the generic infrastructure. And we actually just talk pulses to back here. So right now we're still talking circuits to the backends, but we actually want to go a level lower and basically put everything onto this part over here. Yeah.
Would it be, from your vision, would it be possible to have some sort of a hybrid application that part of this application goes to the quantum compiler based on QIR, and the rest goes to the traditional HPC system, with GPUs and whatever currently accelerators we've got?
So this is certainly possible.
Compilers are going to be integrated.
So right now, we're dealing with an LLVM-based compiler, right? So we can represent classic code and quantum code in one structure. But which one goes where, since the algorithms are so different, isn't still left to the developer, right? It needs to be someone who's willing to develop a quantum and a GPU-based algorithm. And then we can put some machine learning on top of it to pick the right one. That always works, right? But it's not that we can automatically transform algorithms, because it's so different in the way you program that you have to write both, right? And then once you write both, you can of course then do studies which one works better in which scenario, and then you can kind of pick it. You also can pick it based on what's available right now. And also when there's that toolkit, CUDA, NVIDIA with the CUDA, Quantum CUDA, what's it called again? So they have actually a way to kind of map circuits onto GPUs. And that could be a target too. If there's no quantum device available and this is small enough to fit in a GPU, you may be willing to pick that part, right? But again, there would be a quantum algorithm mapped to the CUDA runtime system. QQuantum, thank you. And so this would work, yeah, absolutely. Hopefully. The other part that we're trying to do with this, and I think that's kind of the neat part of this, these blocks here look very separated out. What we really want to do is to have this whole part as a single process linked in, and with that, it automatically runs on the HPC system, right? So you now have the application process with the JIT compiler, with the QDMI backend, all linked together into one binary that's be linked to the MPI application running on the HPC node. And if you have this compiler now properly optimized, using OpenMP itself, using potentially even MPI itself, again, using malleability, requesting additional nodes, right? So you can basically play with all kinds of different things. But once this is all in one environment, we can actually do that. And that's kind of one of the goals that we have. So this whole thing runs directly on the cluster, can then talk directly to the quantum control system, which of course, again, is specific to a modality. But this is kind of our strategy to get the integration going, because we run everything onto a single process on the HPC node, on the HPC environment. Okay, and so towards the end, I want to just mention one other thing. This is all engineering part in the sense. It's cool research, it's engineering, but the other thing we noticed really is the culture part. You have the computer science community and the physics community thinking totally different. Even terminology is different, right? What's a gate? What's an operation? What's a bit, right? As these things are so different, so we kind of really found we need to bring these communities more together. This was the hardest part when we started up the Munich Quantum Valley. How do we get them into one room, talk the same language as that? And so we have been pushing a lot of initiatives in that sense. So we held last year the first European Quantum System Software Summit, where we tried to bring vendors and software developers into one room. This is Reitenhaslach, this is the Turm Cloister, where we can have these meetings in a very nice way. It's very remote, but it's remote as Dachstuhl. But you can use it for that. We already held a second one in July. We're going to have another ones of those coming up, where we bring the European community together with some external observers and advisors as well, of course. But the idea of how can we then make use of these Euro HPC systems, where these different sites get European systems, can we find a common software stack that really works across that? And the last one is a little bit of an advertisement in case people are interested in that. There is actually now a quantum HPC working group as part of the IEEE Quantum Initiative, which has been stood up. We've been working on this together with Oak Ridge, Los Alamos, and iCheck, the Irish Center. So if you're interested in that, we launched it at IEEE Quantum Week with a BOF session at SC. We're planning a whole bunch of more BOFs and events to really bring this community together and get the idea of this quantum HPC going. So that's a growing push, and we're getting a lot of support from the quantum initiatives, which is one of the DOE labs, but also supported by places like rethink and Euro HPC, because this is really, if you don't get this done the right way, I think quantum doesn't have much chance, because we need this integration with HPC. So again, to summarize, it's a software challenge. We need this comprehensive software stack. We need to integrate this into the HPC environment. And also, then this is exactly what we're trying with the Munich Quantum Software Stack, to be portable across these systems, to have these new programming models in there, to enable more efficient compilers and optimizers, and then at some point also get the tools in part, that more right now on the verification side and correctness side, but ultimately also on the optimization side. And before I finish, of course, I have to mention this has been funded by a whole bunch of organizations and also takes a lot of teams. So this is my team at TUM, this is Laura's team at LRZ, which has been doing a lot of the software development work, and this is a group shot of the MQV, the Munich Quantum Valley. In total, there's about 300 scientists working on this project now in Munich. This is not all of them, but it was the last review meeting we had in September, and actually, sorry, wrong, this is 23. This is the picture of the 23 group in that sense. So with that, hope this was interesting. I'm happy to take questions or criticism or suggestions, whatever you want to do with quantum. Thank you.
So clarification here. You had a stack somewhere where you said, oh, use HPC, MPI, GPUs, and then quantum, GPIs. Whatever, GPU, something. The problem with this I see is it gives us the impression that a quantum device is just another tightly integrated GPU, but it isn't. It never will be, because if it's a physical experiment, so forget about superconductors for a moment, even there I think it's very questionable because of the I/O problem, then it's not tightly integrated.
You mean this one?
The question, what about slurs? So really we have to, if we want to tightly integrate it into HPC, my hypothesis is we need to actually come up with a different HPC execution model as well, where you basically say, if I depend on a quantum kernel, I need to have two parts. It's sort of like almost asynchronous execution. I do this, and I get rid of my job, or somehow swap it out and have it wait. Because it could take any amount of time getting the device, or if you have the device ready to read, prepare a state, because the state depends on your top simulation or whatever you have, and then read it out and all that stuff. So even the I/O problem would require you to decouple so that you no longer can tightly integrate this. That came kind of out when you were talking about flux, but the original slide shows it.
Yeah, I was trying to pull it up, but somehow it doesn't show. Sorry. Right? Okay. So you're right. So this one is a simplified version where we're trying to play with the QPI right now if you have existing workflows, right? If you pull this out one level higher and you actually do workflow-based, you want to really consider potentially putting it on a different part, pausing it, doing something else in parallel. So that will be where we get the more fancy scheduling. This is without the fancy scheduling.
But should we still do the MPI? Or should we break it up into something before the QPI and after the QPI call? If you have multiple ones, basically it becomes pieces of a workflow or something.
Well, it depends, right? I mean, MPI in general is a communication mechanism, right? So if you even have I could see even MPI using for larger workflows, and even for pausing you can do with MPI. But in this tightly coupled way, if you assume this is a tightly coupled application with thousands of nodes pounding on the quantum accelerator, it gets a bit more difficult. On the other hand, there are companies out there which are trying to do PCI devices for quantum, where every node could have a quantum computer in it, right? So for those, it may work again. But yeah, right, for the idea of having this one cryostat in the center, this is probably not the right model. That's absolutely right.
I mean, if you think about ion traps or so, you're not going to have like a PCIe card or so. It's physically impossible.
So there's actually ideas of putting these to control on the PCI card, right, and having the quantum system directly plug into that PCI card. Again, you wouldn't have thousands of those, but you would have, right? It's a scaling part, yeah. So the question is which granularity you want to break it up at some point. And I agree with you. This is an experiment we're doing right now. This will probably not work with the larger scale. But on the other hand, the question is, what does the HPC system do when you send something to the quantum computer? And you need a lot of compute to get the quantum computer going. So if you repurpose that, the HPC node is actually not idle, it's preparing your quantum experiment. And the question is, how heavy is this? How much are you using from your node at this point? And if it's too little, then you probably want to get something else and co-schedule something on top of that. But if it's enough, you may actually be able to kind of shorten the latency of the quantum circuit at that point. But that's something to be experimented with.
Maybe one comment, you had something about the classical quantum interaction, like these EQE algorithms and all that stuff. That's today. So that's today when we are looking at noisy quantum computing. Tomorrow, the idea is you're going to have quantum error correction, right? And that also requires classical interaction, but a much tighter one. And I think that would be also interesting to look at and devise a hardware software co-design.
Yeah. And the question is, how close can you pull this into the HPC part? If you do cryotechnology, you have to have a bridge in between. You can't do that as close. For warm ones, you can bring it closer, right?
I don't think HPC will be involved in error correction. That's going to be more of a better problem, because it needs to be as close as you can to the cryostat. And there's temperature issues and all kinds of things. You can't have it everywhere. You have to have it one level above, but you don't want to leave.
So there's I see what you're saying. For me, that's kind of how do you define HPC. I think once you do that, this is high performance computing, right? In that sense, that you have a highly parallel system that does these error corrections from thousands of qubits in a real-time fashion, right? This is kind of high performance in that point, right? It's not your MPI simulation code, that's clear, right? But it is boring from, yeah. It's also high performance at this point, that's certainly right, yeah.
So how long did it take to run the code that generated the histogram on the actual supercomputer?
The experiment that we saw, that took seconds. That was really fast. It's a 5-qubit system. The latency was actually in the scheduling and issuing the thing, not in running it. I mean, these on superconducting, you have really tight around turn. Each shot is very short, and the measurement logic is fairly decent. So we did this live during presentations.
Actually, it's dominated by I/O orders of magnitude. I think at least 2 or 3 orders of magnitude.
Yeah.
Really extremely fast.
Yeah.
Milliseconds.
Yeah, the problem is to read out the physical time to get the data out of the system to do the read, and that's right. That dominated the performance. Yeah. Plus then the software on top of that actually does the processing in Python.
So is the Qiskit thing works for the one? So that one which is currently that is from IBM or it's from IQM?
There's IQM. We don't have an IBM system. They don't sell things. They just want you to rent it for $1 million.
And so the one you showed was Qiskit, so that is generic.
Yeah, so you can do different providers in Qiskit, but then you buy into the whole Qiskit toolchain, which is again dominated by IBM. And for superconducting, it acts fairly well because IBM is dealing with superconducting systems. On other ones, you have to do a little bit more, but there are different providers. But it's all Python-based. They're changing now too. They're doing more and more also in native languages. They're also opening up to the idea of having a more standardized representation, so they're moving in this direction as well. But Qiskit was developed for the IBM systems and then opened up so people can start adding their own things to that. And we're just using the front-end part of having a separate provider to that, where we can target our system with that. All right. Everything is clear, okay. Thank you.